Now that we understand how to do addition, we've made some significant progress. And if the title of this lesson were binary addition circuits, we'd be done. But it's called binary arithmetic circuits. So we need to do more than just addition. We need to do subtraction and then to a lesser extent multiplication and division. The good news is that subtraction, it turns out, is really just addition with negative numbers. So if we wanted to do 100 minus 25 equals 75, what we're really going to do is 100 plus negative 25 equals 75. This means that subtraction is really just, to be able to do subtraction, it really just means that you need to have a thorough understanding of addition circuits and then have an understanding of how to negate a number, how to find the negative of a number. So far, all the numbers that we've ever talked about in this class, all the binary numbers, have been positive. I haven't even given you the hint of the fact that there could be negative numbers, I don't believe, but it turns out that there can. And in fact, there are several different ways to represent negative numbers, but I believe that by far the most common and the best of these methods is called 2's complement. Before we tackle 2's complement, let's look at what unsigned arithmetic looks like. Here we have a number wheel. And if you're like me, middle school was pretty full of number lines. We talked a lot about number lines, but in binary circuits, or I'm sorry, in binary arithmetic, it's often the case that the number of bits is fixed. And if the number of bits is fixed, then it turns out that the numbers are really along a circle, because when you get up to the highest possible number, you wrap back around to the next number, kind of like an odometer wrapping around. And so it's better to represent them as on a circle. And here you can see that we have 0, 0, 0 is 0, 0, 0, 1 is 1, 1, 0, 0 is 4, 1, 1, 0 is 6, 1, 1, 1 is 7. And that really this flows very smoothly when we're doing addition. The only place where it's not smooth is right between 7 and 0. If we ever do an addition that causes us to cross this line right here, then we've probably caused an overflow to occur. And while you don't need to worry too much about overflow in this class, overflow will become important in next year in digital logic. So for now, just be aware of the fact that the numbers are on a number circle instead of a number line, number wheel sometimes it's referred to, and that there's a place where if you cross that line, you're going to have an overflow occur. So what we'd like is we'd like to be able to represent signed arithmetic or a sort of positive and negative arithmetic in such a way that we have a nice, smooth, continuous flow right around 0. From -2 to -1 to 0 to +1 to +2. We'd like that to work well. You know, and if there has to be a place, as there is here, where there's going to be a discontinuity or sort of an overflow point, we don't want it to occur right near 0. We'd like it to occur as far away from 0 as possible. And it turns out that that's one of the strengths of 2's complement. Here you see the number wheel with 2's complement, and look here, right near 0, -2, -1, 0, 1, 2. It's nice and smooth all around 0. There is an overflow point, and that overflow point is between 0, 1, 1 and 1, 0, 0. Because 0, 1, 1 corresponds to a +3 and 1, 0, 0 corresponds to a -4. So there's still a place where you're going to have to wrap around. There's always going to be a place if you have a finite number of bits where there'll have to be an overflow. Again, not a real concern for this semester, but for next semester. But right up in here where we're around 0, which is where we're going to spend most of our time, where quote unquote around 0 can be, you know, plus or minus 10,000 or a million. We're sort of focusing our energy around 0, but usually we've got much more than 3 bits in our number. If we're going to do addition, we're going to go clockwise. If we're going to do subtraction, we're going to tend to go counterclockwise. And really the only thing that's changed here is we still have the same binary numbers, but we've assigned them to different integers out here. So whereas 1, 1, 1 used to be +7, now it's -1. 1, 1, 0 used to be +6, now it's -2. 1, 0, 1 is now -3, 1, 0, 0 is -4. One great thing about this is that all negative numbers start with a 1. So the most significant bit can be used to identify negative numbers, and if the leading number, if the most significant bit is a 0, then you know that the number is either 0 or positive. We refer to that as non-negative. So if the number starts with a 0, then it's going to be non-negative. So you might say, I don't want to have to memorize 1, 1, 1 is -1, 1, 1, 0 is -2. Is there a way to calculate what is the code that would correspond to a negative number? And the answer is yes, there are. Yes, there is. There's a 3-step process. First of all, figure out the binary code for the positive number. So if you want -10, first of all, calculate what is binary for +10. Then, very simple, invert every bit and add 1 to the result. So inverting a binary number, or negating a binary number, can be done by inverting every bit and adding 1 to the result. You might say, why are we adding 1 to the result? Well, that's just the way that we're going to be working with it. If we didn't add 1, we'd be using something called 1's complement arithmetic, but we're going to be using 2's complement arithmetic because that gives us the good result that was shown up here in this number wheel. So let's see an example. If we wanted to do 100 minus 25 equals 75. So we need to first of all find the 2's complement code for negative 25, and then we're going to add that to the positive 100. Now, how many bits are we going to need? Well, 100 is going to need at least 7 bits to represent 100, but to allow for both positive and negative numbers, we're going to use 8 bits. Almost all the time, if you're going to need to do a problem like this, I'll simply tell you how many bits to use. So, first of all, calculate positive 25. Well, you can do this the way that you learned how to do it earlier in the semester, or if at this point, if you'd like to use Google, you can just say 25 in binary, and it will tell you what that is in binary. But it's good to get more practice, so I would encourage you to say, okay, well, let's see, I know that I'm going to need a 16, I'm going to need an 8, and I'm going to need a 1, and that's how you can figure out what 25 would be. Then you invert every bit. So notice that it's simply 0 becomes a 1 becomes a 0, you invert every bit. Then you're going to add 1. Now, adding 1, in this case, only impacted the least significant bit, but realize that it could have carried over to other bits if this first bit had been a 1 right here. You're literally doing an addition. You're just adding 1 to the result. In this case, the leading bit was a 0, so it becomes a 1. And here we see that this is the code that corresponds to a negative 25. It does start with a 1, so we know that it's negative, and it is going to represent negative 25. So let's do 100 minus 25. You can see here's the code for 100. We just found the code for negative 25. I'm going to do 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 1 is 0, carry the 1, 1 plus 0 is 1, 0 plus 0 is 0, 1 plus 1 is 0, carry the 1, 1 plus 1 plus 1 is 1, carry the 1, 1 plus 0 plus 1 is going to give 0, carry the 1, and the 1 is just going to flow right down here. But when you're doing 2's complement arithmetic, you can ignore the carry out. So doing 2's complement addition, we're typically going to ignore this last carry out bit. I know that that's probably confusing and frustrating, but for right now, just know that if you're doing regular binary addition, you consider this one. If you're not, then you don't. If you're doing 2's complement addition, then you would just omit or ignore this last bit. So if we look here at what does this number in the box represent, well, that number is a 60. Let's see, that's going to be a 64 plus an 8 plus a 2 plus a 1. That'd be 75. And so sure enough, 100 minus 25 yields 75. So we're feeling pretty good about this. We can now represent positive numbers, we can represent negative numbers, we can do addition, we can do subtraction. We found out that addition or subtraction is really just addition but with a negative number. So once we have the ability to negate a number, we've opened up our horizons from just addition to include subtraction. Time to do an example. Do the 2's complement arithmetic example problem. We'll come back and we'll discuss multiplication and division at least a little bit so you have a hint of how multiplication and division are performed.